Alright, so we've done confidence intervals and hypothesis testing proportions. Now we'll do means. So these are the formulas here. So if you know the standard deviation of the population, you can use Z, which for proportions we basically do. For probability type stuff, for decks of cards, rolling a die and all that. But typically for mean, you don't know that. So you use Gossett's number T instead of Z. So you can use Z or T for basically proportions or means, but typically you'd always want to use Z for proportions and then T for means, because doing so otherwise would be very abnormal out there, cases that aren't going to come up very much. So the n plus 1, that should be minus 1. Whoops. Oh, well, it's a typo. We'll fix that after. Minus, there we go. That's our degrees of freedom, basically. Alright, so let's take these numbers here and do a confidence interval, right? So these are the hours of sleep. So we'll pull up our spreadsheet, we'll pull up a new tab. So we're going to rename this as part 1. And on the new tab, rename this as part 2. Blow it up. Paste, oh boy. Can we get paste without? Paste special, values only. Alright, I don't want the formatting crap. We don't want that. Alright, so I'll put all these in a single, whoops. Put all these in a single column. Okay, so we want sample mean, sample standard deviation. Alright, let's link those together, merge them, and merge them. Okay. Alright, so we're going to add up all the values, going to add them all up. There's 25 of them, so we're going to divide it by 25. So there's a sample mean. Alright, and then standard deviation dot. And you notice if you just put standard deviation, there is one there. Okay, and then there's population, and then there's sample. So dot S is what we want, because this is obviously a sample, not every single value. And there we go. Okay. Okay, so let's go back and start typing here. Okay, so the sample standard deviation was, well, that was approximate, obviously. 1.075, I believe. We'll look at that in a minute. And then the mean sample was, I think, exactly 6.64, wasn't it? Let's take a look. Let me go back. Yes, that was an exact answer, right? You can make it bigger. Whereas the other one is an approximation. Okay. So there's our sample standard deviation. There's our sample mean, right? X bar is the sample one, and lowercase s is the sample one. All right. So t underscore 25 minus 1 equals, I believe it's t dot inverse, and you're wondering why is it 25 minus 1? Well, there's 25 samples and degrees of freedom. So this is our degrees of freedom essentially right here. 25 minus 1. Okay, so what do we use for this value here? Well, it's a 90% confidence interval. Alright, so we draw our picture here. There's our 90% confidence, right? So our true population answer will fall 90% of the time in here, and then 5% here, and 5% here, right? So we have to go 95 to get to there, right? So 5 plus there, right? So these are our t values. There's a t value there. There's a t value there. So same calculation as the z essentially as far as how we do it. Comma 25 minus 1. Okay. And approximate. Okay, so let's go to our spreadsheet here. Alright, so degrees of freedom, right, is 24, right? 25 minus 1. Our t value is t dot inverse 0.95, comma, degrees of freedom. Alright, so we get about 1.7 whatever it is, right? 1.71 something, whatever it is, doesn't really matter. Okay, so we want to do the confidence interval now. That's the first things we need to do that. So there it is. I'm going to copy that and go to there. Alright, so our sample was 6.64 minus, alright, so this was 1.71 dot dot dot, and this was 25 samples, right? So our true population mean, right, because this is the population mean, that is the sample mean. The sample might be the population, might be more, might be less. We don't really know. We'll put a plus there. Okay. So now we can do our confidence interval in the right here, right? So it is our mean minus the t value times parentheses the standard deviation divided by the square root of 25, right? So we'll take that. We're going to copy it. Copy. Paste. Change that to a plus. Okay. So there's our confidence interval. So we get 6.27 dot dot dot. Copy. And 7.008 dot dot dot, I believe. And these are hours of sleep. So there's our confidence interval. So basically what are we saying in context? In context. We are 90% confident the true population mean for the number of hours the students sleep is in the interval, right? So the true population, what actually is in there somewhere, right? Our mean is 6.64, but we don't know if that matches the population or not. We think it's in there. So so basically 10% of the time it's not going to be in there. Oh, whoops. Okay. So let's do a hypothesis test. Alright, so since the recommended hours is sleep 7 or more, students at this school getting the minimum number of hours of 7 sleep. Okay. So step 1, the parameter of interest is not a proportion now, it is a mean. So population mean. Mean number of hours of sleep for a student. And then this will be a 1 sample t-test for the mean number of hours of sleep for a student. right? So we're doing t not z because this is a mean. We don't know the population standard deviation. That's why I use t. Okay, so make this bold. H sub 0, H sub A. Okay, so the mean is 7. That's what they're supposed to get, right? Well, 7 or more, but you never put the greater part or less than part as far as the null goes. So you just put the equals. So here, this one would be less than 7, right? Hours. So you want to put hours in hours. You're like, well, we never labeled these before. Well, yes. When you did proportions, they were just proportions, right? They didn't need a label. These are means, so they're nouns, so you need a label. Okay, so that's what we're doing. Okay, all right, step 2. Step 2, can we do it? All right. All right, so the S was approximately, oh boy, was 1.07 dot dot dot, and the number of samples was 25, right? The mean expected for the samples, X samples, the mean of the samples is 7, right? And the, let's say that, we'll copy this. Change that to standard deviation. So the standard error equals, right, the ratio, the 1.07 dot 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 over 25. Okay, what that works out to be. Okay. So the samples are likely independent because they are not likely to take the survey twice. There is no reason to believe they were not collected randomly, right? Because they'd be independent and random. Okay, and then if you look at the data on the graph, the data appears to be unimodal and normal when you create a histogram. Okay, so you're welcome to graph the data if you want, but it looks approximately normal, because if it doesn't, you have a problem, right? So with mean data, you have to be independent and random, has to be unimodal or normal. Okay, so step 3. So what are we doing? Can we do it? Let's do it. So step 3, oops, let's put the 3 in there. Okay, so so the mean for the sample that we calculated was what, 6.64, right? So T sub 24 is, so you go back and do the formula on the other page, it's the mean minus the mean, right? Standard error, right? Standard error. So basically, observed minus expected over standard deviation, right? So 6.64 minus the 7 over the where the standard error works out to be, right? That's going to give us some kind of t-value. As to what that is, not too sure. Let's figure that out now. Okay. So standard error. Let's get that done first, right? So that is the standard deviation of the data divided by the square root of 25, right? So it's a standard deviation accounted for the critical accounted for by the sample size. Okay, so we need the t-value. All right, so our t-value is going to be our mean minus, it was 7 was the hypothesized value, divided by the standard error. Okay, so negative 1.67. Negative 1.67 dot dot dot. Okay, we're good there. So the area is equal to t dot distribution, I believe. Don't quote me on that. I'm going to put the t value in, comma, 25 minus 1. That'll give us an area. Okay, we'll check that in a minute. Alright, so if we think about what we have here, we have a negative t. It's a negative t, right? It's a negative t value right there. And we want a less than case, so that means we want this over here, correct? So we're already set up correctly. We don't need to do any 1 minuses or anything, or doubling it. Because if it was a 2-tail, I'd have to double it. But it's not a 2-tail, so I don't need to double it. And I don't have to do 1 minus because we don't want this end. So it's just this end here, so I don't need to do that. Okay, so let's go to the spreadsheet here. So we'll do the area. Alright, so t dot distribution. Oh, that is there, okay. So we want to put in the t value, which is right there. Nope, right there, comma, 25 minus 1. Okay, it's 25 samples, right? Ooh, what did we do wrong here? I don't know what we did wrong. We'll try it again. Equals normal. No, t dot distribution. Okay, we want C8, comma. Oh, I know what we forgot, because it says right here. You want the x value, that's just the t, degrees of freedom, which is 25 minus 1. And then obviously cumulative, we have to put true. So we want to add up all the values left to right. Because if you actually look at it, as you type it, it actually tells you it's a left tail. So a little pop-up tells you what to do, essentially, if you don't remember. Okay, so we get 0.05359, as I believe was what I saw. Just double check. 05359, 05359. There's a 1 in there, but it doesn't really matter. Okay, so so that is, if I think about it, that is the p-value, right? The probability value. So the area is probability. The probability is area, essentially, under the curve. Okay, so step 4. Step 4, right? Because what we're doing, can we do it? We'll do it, and then analyze the findings after. Okay, so what did we find, essentially? We found a p-value that is greater than alpha, which is 5, right? So we're going to do not reject the null hypothesis. Okay. All right, so let's go through a couple things. We got 0.05, which is clearly bigger than 5. So again, why did I use a 5 here? Well, if I go back to my confidence interval, it was 90%. That's for a 2-tail, right? So my confidence interval was 90%, right? Which means 5% of the time it's going to be too low, 5% of the time it's going to be too high for the real answer, what the population actually is. But the problem is our hypothesis test was only a 1-tail. So although alpha here is 10%, right? The alpha for the hypothesis test is 0.05 because the confidence interval is two tail. The hypothesis test is only one tail, right? They relate to each other, right? So we change the alpha down there. Okay. So essentially, um, our sample mean is not significant. Since we did not reject the null hypothesis, the area was very large, right? So you can think of it this way, right? This is 0.05. Our value is more than 0.05, so we're in this region over here. We're not in the shaded region. It wasn't significant. So these are all common samples over here, right? If I actually made it to here, which means I'm less than, that'd be a significant sample. Our sample mean is not significant. Okay. There is not enough evidence to reject the null hypothesis. Because if he did, it would be in that region, basically. So in context, it is likely true that the students are getting at least 7 hours of sleep at this school. Okay, notice how I'm kind of hedging my bet because you don't ever know for sure, right? None of these things are they're our best guess essentially. We don't ever know for sure, right? So what could have happened here is this test has a likely type 2 error because we did not reject the null hypothesis. Okay, so we did not reject it. Maybe we should have, right? This appears to be likely because the p-value is close to alpha, right? And, right, so look, so 0.053, 0.05, that's really close. And let's see, so our hypothesis test was 7 hours. Let's go back to here. Ooh, 7.008, that's really close to the confidence interval, right? And the hypothesized value is just barely inside the confidence interval. Okay, so it's very, very close. So there might be a type 2, or maybe not. Maybe there is, maybe there not. We don't never know for sure, but it's certainly leaning towards like there could be one here. Okay. All right. Let's do one more. So this one doesn't look normal, but it's close enough, right? So that means it's good. Okay. So 150-hour raised salmon of organic contaminants. The researcher found the mean concentration of carcinogenic insecticide Mirarex to be this right here in parts per million with a standard deviation of this. That's a sample. As a safety recommendation to recreational fishers, the EPA recommended a max value of 0.08 parts per million. The farm salmon came beyond the EPA's permitted amount, created 95% confidence interval, carry out the hypothesis test. Okay. All right. So basically, we're saying the standard deviation is 0.0495, right? And the mean is 0. Scroll up, 0.913. Okay, so those were given to us. So I don't actually need to calculate them this time. Saves us a little bit of time. All right, so we need T sub 150 minus 1, or 149 essentially, correct? It says 150 samples? Yes, 150 samples. Okay. So T dot inverse, parentheses. Okay, so we want a 95% confidence interval, right? So it's a 95% confidence interval. That means we have 2.5 on either end, 0.02 on this side and 0.02 on that side, right? So you're going to add those together because you're going from here to here to get the t, right? So if I add that together, it gives me what? 97.5, so 0.975 comma 150 minus 1 gives me my t value, right? And then I can do my confidence interval at that point, which I'm going to steal. So we don't know what this is, but we'll come back to it. I'm going to steal my confidence interval from back here, so I don't have to retype it. Right? Okay, so let's do that. Go back to here. Let's just do t equals, excuse me, t dot inverse 0.975 comma 150 minus 1. Right? Okay, so 1.97 is our t value, 19976. That's good enough. Okay, whoop, that's the wrong one. 1.976. Dot dot dot. Alright, confidence interval. So our confidence interval is 0.0913 minus this garbage right here. Standard deviation was 0.495, and the sample size was 150, right? So where is our true population mean? I don't know. So we're going to copy, paste, change that to plus. Okay. All right, let's put that in our spreadsheet now. So we want our sample mean, sample standard deviation, right? We'll merge those and merge those. So this was 0.0913, 0.0495, right? Okay, so that's all I need. I got my t. Yeah. Okay, so equals the mean minus the t value times the standard deviation divided by the square root of, it was what, 150 here, right? 150, close, close. I think I got it. Then I'm going to copy it and paste it and change that to a plus. So here's my confidence interval, so 99833. 99833. Okay, so let's go back to here. So I got, when I did this, 0.0833 dot dot dot, and then 0.0993 dot dot dot, and these are parts per million, right? So again, these are nouns. I don't know if it's uppercase or not. I think it's lowercase, actually. Let me just, parts per million. Parts per million. All right. So if the hypothesis test rejects, it will not be in there. If it doesn't reject, it will be in there as far as what's being hypothesized. So 0.08 is the EPA amount, basically. So if you're more than that, then you have a problem, correct? Okay. So step 1. The parameter of interest mu parts per million of insecticide. Probably should put Murex insecticide maybe, but oh well. So this will be a 1 sample t-test for the mean parts per million of insecticide. Probably should specify Murex, but that's fine. Okay. So bold the null hypothesis, the alternative hypothesis. So the mean, nope, that's not the correct. Mu equals 0.08 parts per million. I'm going to copy that to save some time. Remember, it's a noun, so you got to label it. So if it's more than that, because if it's less than or equal to, it's fine, right? Because technically there's a less than here, right? Because if it's less than, you're fine. The problem is if it's greater than, so you have to assume it's fine, and that's unless you find the evidence to prove otherwise, right? Okay, so that's what we're doing. Step 2, can we do it? Okay, so step 2, the standard deviation is 0.0495. The number of samples is 150. The mean for the samples, the sample mean essentially, is 0.08. And then we'll copy this, change that to standard deviation. Right, or standard error. Do that. So 0.0495 divided by, I'm sorry, why did I put the whole thing in a square root? I don't know why I did that. Sorry. 0.0495 divided by the square root of 150. Don't know exactly what that is, but that's fine. Okay, so those are the sample ones when you have 150 of them. So the samples are likely independent because you are not likely to return a salmon after testing, because obviously you're cutting these up, and the 150 is less than 10% of the population, which means it's independent because it's not going to affect the probability, basically. The data appears unimodal and normal when you create the histogram. Okay. Oops, I spelled unimodal wrong. And there is no reason to believe the salmon are not selected randomly. Right, so the data has to be selected randomly, it has to be independent, and it has to be normal. Okay. Okay, step 3, let's actually do it now. So, the mean is actually 0.0913, right? So when I do t sub 149, or, right, essentially you're going to get 0.09113 minus 0.08, right? Right, sample minus observed minus expected, sample minus population, right? Okay, and then the standard error, right, which we have up here. As to what that is, who knows? We'll figure that out in a minute. And then we'll use that to get the area, which is equal to t dot distribution. And then we'll do t. We're going to do a modification here. 150 minus 1 comma true. Let's have to modify this though. We'll talk about that after. Let's go to our spreadsheet. Okay, so t again, right? So the mean minus the sample. Oh, we should do the standard error. Let's do the standard error first. I didn't do that. Standard error. Okay, so that is the standard deviation divided by the square root of sample size. Right? Okay, now we can do the t. Okay, let's see. So we have the mean minus 0.08, so the expected, or the observed minus expected divided by the standard error. So there's our t value, 2.79. Okay, we can put that back in here if we want. So 2.79 dot 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 keeps going. Okay, so now we'll do our area in the spreadsheet here, but area equals. So here's the thing. If I do t dot distribution, and I do the t value, comma, the 150 minus 1, comma, true, it's a question of is this the right value or not, right? So t value, 150 minus 1, true. So I get 0.99, right? Well, here's the thing, though. Let's go back to our hypothesis test. This is a greater than 1, right? It's a right tail. So the reality is, that's my t value here, right? 2.79. I want this area up here. But if I do this, it reads left to right, correct? So I need to do a 1 minus here, don't I? So I need to do 1 minus, and we'll get an approximate value. All right, let's go back to our spreadsheet and do 1 minus, so 0.0029, I guess. 0.0029 dot dot dot. Okay, so the question is, what is our alpha, right? So we need to go to step 4. Step 4. So if we do this, whoops, the p-value is less than alpha, because alpha in this case is 0.025, so we're going to reject the null hypothesis. So how the hell did I get 0.025? Well, let's take a look here. The confidence interval was 95%, right? .95, right? So that means 0.25 here, 0.25. That's my alpha. And 0.025. So the confidence interval alpha is 0.05, right? Because 5% chance the value will not be in our confidence interval. But our hypothesis test was a one tail. So it's only this alpha here, right? So the confidence interval was alpha. This is its alpha. But the hypothesis test is this one because it's only one of the tails. Confidence interval is two tails. So 2.529, that's very close. But clearly, wait a minute. I did that backwards, I believe. No, it was 0029, wasn't it? 0029. That's clearly less. I was thinking 10. That's clearly less than that. Okay. So, since we rejected it, our sample mean is significant and not likely to occur. So basically we're in the shaded region, right? It's not one of the common samples. So there is enough evidence to reject the null hypothesis. Okay, so in context, you must, so it is likely, the amount of is of murex, right? is over the EPA limit. So basically you assume that was not over until you prove otherwise, which we did prove essentially. And I put likely because, again, you never know for sure, because this test has a likely type 1 error because we did not reject the null hypothesis. I don't know if it's likely. I would say it could have. Could have a type 1 error. Okay. So if you look at it, right, since we did reject it, it's not going to be in the confidence interval, right? So is 8% in the confidence interval, or 8 parts per million? It is not in there, right? It's falling outside of it, isn't it? Okay. So, the p value is not close to alpha, and the hypothesized value is not in the confidence interval. Okay. All right, that's the end of that part.